Physics 105, Chapter 6. We'll be studying uniform circular motion again, or just more, orbits and gravity. I apologize for the setup. We're sort of cut off a little bit, but we won't see that on very many slides. Objectives. We want to extend our understanding of the kinematics of circular motion beyond the basics presented in Chapter 3. We'll apply Newton's laws for circular motion. We'll solve a range of problems. We'll understand circular orbits of satellites and planets as another case of circular motion, and we'll develop an understanding of the long-range force of gravity. All right, so we've already talked about this, but we'll talk about it again. What is uniform circular motion? Well, it just means constant speed, but obviously the direction is constantly changing. So that's why it's called uniform, because the speed is uniform. But the velocity is not uniform, because the velocity includes the direction. Now, we've seen this many, many times. An object undergoes uniform circular motion as shown. Use vector subtraction to find the direction of the acceleration at point A. So how did we do that? We said that the direction of A equals the direction of delta V, which is the direction of V final minus V initial. And if we want the acceleration at A, this is like V final, it's V after. This is V initial, it's V before. So you just do that vector subtraction, which we've done a million times. So here's V after, here's minus V before, so bingo. All right, so this is not a surprise. The acceleration vector always points towards the center of the circle. And because that's kind of special, we're going to give it a name. Now, you might think this is a center, but that's not what it is. It's C stands for centripetal. But centripetal means center seeking. So, if you want to think of it as center, go right ahead. That's great. Now, what does this acceleration do? Well, the speed is constant, so all this acceleration does is change the direction of motion. And we've seen this before. The centripetal acceleration always is perpendicular to the velocity everywhere. And here's an important formula, and I would recommend you memorize this. I'll put it on the equation sheet, but we're just going to use it a lot. We're actually even going to use it in Physics 106. So, and the derivation is in the book. The centripetal acceleration equals the velocity squared over the radius. And again, of course, it's towards the center of the circle. All right. Some other terms for you. What is the period? So let's say we're talking about a planet orbiting a star. So the period is the time for one orbit. If you have a grandfather's clock, this is the period. It's the time for one, I don't want to say orbit, but revolution or something like that. Cycle, right? Start here, go like that, right? So it's a time for one cycle, one orbit, one revolution, whatever you want to call it. Now, the period, so it's a time, right? It's a time. Time for one orbit or whatever you want to call it. So they use uppercase T, which is actually great because it's a time, but it's a special time, right? It's a time for one cycle. So uppercase T. And of course, the units are seconds because it's time. What's frequency? Frequency is how many cycles per second. How many cycles per second? So frequency, which is F, is just 1 over the period. That's all. Now, what are the units? Well, the units are 1 over seconds. So you can just say that's seconds to the negative 1 power. But you know how we do things in physics. We always name things after famous physicists who are deceased. So that's called a Hertz, named after Mr. Hertz, of course, right? Which is not the rental car company. Okay. All right. So okay, let's do the grandfather's clock again. Let's say it takes 1 second to make a cycle. 1 second. Well, let's say 2. Yeah, 2 seconds. Okay. All right. So 2 seconds to make 1 cycle. Right. So the period is 2 seconds. So therefore, if it takes 2 seconds to make the complete period, how many cycles do I make in 1 second? Well, half, right? Because it takes 2 seconds, so 1 second, 2 seconds. So how many cycles did I do in a second? Just 1 half. And again, that's just from the period, the formula, right? T is 1 over F, which is 1 over 2 seconds, which is 0.5 hertz. Oops. Okay, all right. Now, we want to get an equation using this stuff for circular motion. Okay. So, let's go back to basics. Velocity is the change in distance over the change in time. All right, no kidding. Now, let's suppose that the time is a period, 1 period. Okay? Well, we're talking about circular motion, right? So if the time is a period, that means we're undergoing, that the object is going around the circle once. Well, what is this distance? It's the circumference of a circle, and the circumference of a circle is 2 pi r, right? 2 pi times the radius of a circle. So that means if we're going to say that the time is a period, we have to say that the distance is one, is a circumference. So it's 2 pi r. All right, great. Now, remember 1 over the period is the frequency. So if we feel like it, we can say that's 2 pi r f. Okay? We're going to use that later on. Don't worry. Okay, so there you go, all right? So the velocity for uniform circular motion, 2 pi r over the period, which is 2 pi r f. And we will use that. So keep that in the back of your head. So velocity is 2 pi r f. Okay, now I'm going to do some demonstrations. Not really. I'm just going to pretend I'm doing demonstrations. So if we were in McKay 134, I would do this, but we're not, so use your imagination. Okay, so this is a metal hoop. So pretend I have this metal hoop on the countertop. And then this is a little piece of wood, this high, that diameter like this, cylindrical piece of wood. This is a piece of string. So what I do, I just take that string and I just kind of go like that. And so this wood, it goes around the circle. All right? So, all right, there you go. All right? So again, you're looking down on a tabletop and you're seeing this piece of wood just go around and around and around. And we're going to ignore friction, of course. All right, so what are the forces on the block? So pause your video and get ready to vote. Okay. And again, here's the picture. All right, so what are they? Well, okay. So this is what it looks like if we're looking down, right? And so there's the tension. Then obviously there's the normal force, and there's weight. That's it, right? Now what is this? Force of motion. I have no idea. No such thing. It's called a distractor. All right, it's garbage. All right, how do the two vertical forces compare? Well, you know, the block of wood stays on the table, right? So the normal force has to equal the weight. Now you're supposed to do that. I don't know why I just answered that, but that's all right. Okay, therefore, what's the net force? So pause your video and answer the question. All right, so if these forces cancel, the net force is the tension. Gee, you didn't see that, right? What is the direction of the net force? Well, you know that also, right? It's towards the center of the circle, right? So the net force is toward the center of the circle. So therefore, there has to be a centripetal force. So I really should have a little c here. Okay. Okay, now what's Newton's second law? F equals ma. So the sum of all those centripetal forces equals ma centripetal. But what's a centripetal? It's v squared over r. So this equals mv squared over r. So this is always going to be true for uniform circular motion. If it's going in a circle, there has to be something that causes it to go in a circle, right? There has to be a force that causes, there's an acceleration towards the center of the circle, F equals ma, so there has to be a force towards the center of the circle. So this is always going to be true. Always, always, always for circular motion. All right, let's do another demonstration. Okay, so here's that same metal ring. And now I take a metal, steel ball. I just kind of shoot it, you know? And so what does it do? This goes around, right? This goes around. And again, you're looking down on the tabletop, right? So you're seeing this ball go around and around and around and around. All right. Same questions. What are the forces on the ball? Pause your video and answer it. Okay, let's be back. Okay, there's no string, right? There's no string. Well, wait a second. This silly ball is going in a circle. What's causing it to go in a circle? The normal force from the metal ring on the metal ball. If that metal ring were not there, would the ball go in a circle? Of course not, just go straight. So there's a normal force that the hoop exerts on the ball. There's a normal force that the countertop exerts on the ball. And of course, there's weight. So three forces. What is the net force? So we're skipping. What's the net force? Well, obviously, this normal force is canceled by gravity. So the net vertical force is 0, and no kidding, because it's not accelerating in the vertical direction. So the net force is the normal force that the hoop exerts on the ball. All right. So what's the direction of that silly thing? Well, it's going in a circle, so it has to be the direction towards the center of the circle. Therefore, the sum of the centripetal forces equals ma centripetal, which equals mv squared over r. Okay, let's beat this to death. Okay, this is not to scale, right? So here's a satellite that orbits Earth. What's the force that causes that satellite to go in a circle around the Earth? Gravity. What's the direction of the gravitational force that the Earth exerts on the satellite? Towards the center of the Earth. Therefore, what's the next slide going to be? Ta-da! All right? So there has to be, so the sum of centripetal forces equals mac equals mv squared over r. By the way, you know, I'm writing this on purpose. I mean, for the examples we've done so far, there's only been one. But pretty soon, there's going to be more than one centripetal force. So I just kind of want to put that in your head, all right? There's not always going to be one. There may be two or more. But I don't care how many there are. This is always, always true for circular motion. Always true. So it's important. Okay, now. Oh, not yet. No, not yet. Okay, so what do we care? How do we use this? Well, like I said, this is always true. So what our job is we have to figure out what are the centripetal forces. Okay? I mean, this is always true, so just write it down. Whoopee! But then we have to put an equal sign here and figure out what the centripetal forces are. And then we can make some progress. You know, it could be gravity, could be normal, could be electricity, could be magnetism. Who knows, you know? But that's our job, to figure it out. So here's a nice example. A block is placed on a turntable that rotates at a fixed angular velocity omega. Given omega, mu s, you know, the coefficient of static friction, mu k, and the mass, how far can the block be placed from the center of the turntable before it slips? This should have said a block of mass m is placed on a turntable. So, sorry, I have to fix that. Okay, so let's do it. Alrighty, so first step, right? Force diagram. No surprise there. So, all right, now, this is the center of the circle, okay? So this is the normal force, that's the weight. Now, what is holding this block in place? I mean, why isn't it going, you know, why isn't it sliding off somewhere? In other words, if this were ice, would the block stay put? Probably not. So what's the force? You know, this thing is going around and around, right? So what's the force that's keeping that thing on? Well, friction, right? Friction. And so it says how far can it be placed? So we want Fs max. So this is Fs max, okay? And again, it points towards the center, right? The centripetal forces point towards the center. So that's not a big surprise. All right, so let's do it. By the way, this is the z-axis. All right, that's the z-axis, right? You can call it whatever you want, doesn't really matter. So the sum, this is nothing new here. The sum of the z-axis, n minus mg, and it's 0, right? It's not accelerating up and down. Okay, so therefore, n equals mg. Now, why did I do that? Because there's friction in the problem. And like we talked about previously, whenever there's friction in the problem, you know that the force of friction is proportional to n, so you got to solve for n. All right, now let's do this. Let's do this. Okay, so the sum, now look at, so the sum of the centripetal forces equals mv squared over r. Okay, now that's totally true, right? I could have written the sum of the centripetal forces equals mac, which equals mv squared or whatever. This is good enough though. Okay, so this is always true.